In the surveillance region, sensor detects measurements originated from the target as well as various unwanted sources which generate collector measurements. So there is no prior information about target existence. So in this collector environment, the target measurements are uncertain and they are available with low detection probability. So it becomes difficult to detect a number of targets. So in this environment, we initialize the tracks using sensor measurement in each scan, which result in the true tracks and the false track. So true tracks are target track and false track are collector. So the tracking system uses the false track discrimination to identify true tracks and false tracks. So in the multi-target tracking trackers, for example, joint integrated probabilistic data association creates all feasible joint measurement to track measurements and evaluates their a posteriori probabilities, which makes the algorithm more complex due to a growing number of feasible joint measurements because it is in the multi-target tracking system the tracks receive the multiple measurements from the multiple targets. So we use we apply linear multi-target in this algorithm, which bypasses the entire process of joint data association by modifying the collector measurement density with the measurement density of the foreign target. It means when updating one track, the other tracks are assumed to be a collector. So in this way, the LMIPDA uh, behave like a single target tracking. So in this paper, in this conference, we apply the smoothing in the linear multi-target tracking based on the IPDA. IPDA is just like a single target tracker integrated probabilistic data association. So LMIPDA basically non-smoothing, which uses only current scan measurement to update the track, but we apply smoothing, which use future scan measurement to improve the target state estimation in past scan, which reduces estimation error. So this work utilizes smoothing and linear multi-target IPDA. Uh, so this refer is SLMIPDA operates tracking in two-way direction, forward direction and backward direction. So here backward tracks are initialized and estimated using all sensor measurements. However, on the other hand side, forward tracks are initialized using sensor measurement, but they are estimated using smoothing measurement. Means after the fusion and smoothing, the forward track are estimated using the smoothing measurement and data association probabilities. So this is our target model. The target model is use the state propagation matrix F to update the target state from previous scan to the current scan, and this is the YK is the sensor measurement equation, and tau is level of the track as well as the target. So we apply the smoothing interval, and so this is the smoothing interval, which is a sequence of corresponding measurement set. So we apply a forward tracking and backward tracking and then fusion, and this is the collector measurement density, the intensity of the measurement, that how many collector measurements are involved in the surveillance region. So first, after initialization, the state probability density function of the target is applied to come up with the prediction, and then we calculate the likelihood function. Then the this is the prior probability that the selected measurement is a target is detected from the target is given by this equation, and then we finally calculate we modify the collector measurement. The collector measurement modifies the measurement density of the number tracks. Means the collector measurement is modifies the detection from other target with the modified collector measurement density, like this one. This is the modified collector measurement density, which calculate the likelihood ratio of the target detection for the current track. This this sigma is the other track. So by making the other track here as a collector, this update the track, the current track, by using the likelihood ratio of the tau track, and to calculate the data association probabilities of the backward tracks as well as the summative tracks, using the using equation number 9. So the estimated track state and target existence probabilities are obtained from 4 and applied here in this equation. The forward and backward prediction are fused to obtain this smoothing prediction by using this formula. And finally, the SLM IPDA track output is applied by using the data association probabilities in the Kalman filter to obtain the total uh, Gaussian sum of one PDF. This is the overall structure for the smoothing. Uh, this smoothing structure is like first apply the backward tracking, for example, scan number 8 to scan number 1, and then we apply the backward tracking, for example, scan number 8 to scan number 1. So the scan first two scans of every interval of every interval used for track initialization, for example here and here and so on. So the after backward estimation, backward track arrive here at scan number 1, then fusion is applied. Here forward track is initialized using scan number 1 and 2, and then for example the prediction, the state PDF is obtained scan number 3 using the forward track initialization from scan number 1 and 2. Here after this track shows the fusion. After fusion, the summating is applied, and then using the summating measurement, the forward track are updated. So only the first four scan are smoothed, and the forward track are estimated in the first four scan, and then the next scan is overlap to the previous interval like this one. So the next interval is again start from 12 to up to 5, then the from 5 to scan number 8 are smoothed after fusion, and then forward strike are estimated in this interval, and this will continue and so on. So every time in each interval, four scan are smoothed and then applied for the statics calculation, and then four new scan are appended in the interval to calculate the next interval smoothing. So this is the block diagram. The, this fusion block receive the backward estimation, multiple backward prediction here, and then here also fusion block receive the forward prediction. So after fusion, the fusion state is smoothed using SLM IPDA, and then the smoothing is send the data association probability and smoothing measurement to the forward block, which estimate the forward tracks in this equation, and then it propagates the forward estimation to the next scan, and then this continues in the fusion block and then smoothing, and finally in each scan the forward confirm to track calculates the confirm the true track, and to check the the SLM IPD output is near the target state or not. This is the target value true state, and this is smoothing state, and here the final output confirmed to track. So here in the simulation result, only the confirmed to track result are shown like this. So there are five multiple targets. So this table shows initial position of all targets, and this is a five target, and the proposed algorithm accurately tracks the multiple targets in the collector environment. These small dots are collector. This is the simulation parameter like surveillance area, collector density, detection probability, and getting probability. This one measurement noise. There are chances scan and 500 runs. And this shows the confirmed. This figure number 3 shows the confirmed contract, which shows the highest number of proposed outcomes. So highest SLMIPA shows the highest number of confirmed to track as compared to executing track, and also RMSC, the proposed algorithm has a lower estimation error as compared to the other executing algorithms. So the confirmation threshold of the algorithms is adjusted to evaluate similar number of confirmed false track, that is 35 out of 500 runs. This is for a fair comparison, and also the probability of target existence is updated using the state transition probability of 0.98 to automatically maintain and propagate the tracks. So this probability of target existence is updated in each track to determine the trackability measure. So this paper verifies the essence of the algorithm, showing that association approach into IPD algorithm. This is the first time in the literature that we applied something in LMIPDA, which significantly improved accuracy in target trajectories and FTT as compared to existing algorithm. So, in future, this research work will be implemented for tracking multi-UAVs in the real-time radar tracking systems. Thank you. These are the references. Thank you.